Assalamu alaikum, everyone. Good morning. In the last class, we were talking about classifications of elementary chemical reactions, and we looked at a huge variety of classifications, right, in terms of the kind of reactions you have in terms of the phase. We spoke about uh, the consecutive reactions, we spoke about competitive reactions, we spoke about first order reactions, and so on and so forth. Now we'll talk about the last classification, which is basically on the type of chain reactions. Okay, so first let's talk about what is a chain reaction, and then we talk about the types of chain reaction. Now, chain reaction, when we talk about chain reaction, it basically involves the production of a radical or an intermediate species. Now, what exactly is a radical? A radical or an intermediate species basically is a species which is very, very reactive. And this speeds up the reaction whenever it is produced in larger quantities, or a net positive radical production always speeds up the reaction. Now, when we talk about a chain reaction, broadly speaking, you have a set of chain reactions, right? So you don't have one reaction, but a set of reactions within a certain chain. And when you look at the overall chain reaction, for the overall chain reaction, the radical species are first produced in the first step, and then it reacts and it produces another radical, sometimes more, and it goes on until the chain terminates when two radicals combine to form a stable species. So it starts with a stable species, ends with a stable species. But the first place where it starts, you create a radical species from stable species, right? So this is how it works out. So when we look at overall when we look at the types of chain reaction, we can classify them on the basis of the net number of radicals that are being produced, right? So you have radicals on the reactant side, you have radicals on the product side. The idea is overall, are we producing radicals? Are there more radicals on the product side? Or are there less radicals on the product side? Based on that comparison of radicals, based on the net number of radicals that we have in a given reaction, we can classify the chain reaction into multiple types. Chain reactions are extremely common, but also a bit complex. Okay, so they have their own complicated rate expressions because of the fact that they happen in a certain chain, right? And to some extent, they are consecutive, not always, but some are consecutive. And we study about chain reactions simply because they are extremely important for combustion. In fact, combustion would not exist the way it exists if there is no chain reactions. Now, when we talk about chain reactions, in chain reactions, the intermediates or radicals are also called as chain carriers. These are the ones that carry the chain, right? And they start the chain, and then when the radicals are gone, that's when the chain ends. That's when the chain terminates. Okay, so we can say that in combustion, the chain carriers are typically the radicals. Radicals are species such as OH, O, HO2, unstable species, basically reactive species, right? So these are typically the chain carriers, but you could have positive or negative ions also as the chain carriers. Positive ions, something like CS3 plus or C3S3 plus. These are going to be in really, really small quantities, but these are all also chain carriers. Okay. Now, if you just think about the chain reaction from a different perspective, well, when you talk about nuclear reaction, then in a nuclear fission, the neutrons are the chain carriers, but in combustion, the radicals are the chain carriers. So now let's look at different types of a chain reaction. So when you talk about a chain reaction, it has certain types, right? Essentially, depending on what is really happening in the reaction. So when we talk about the chain reaction, it starts with what is called as an initiation reaction. Okay, this is where we have a stable species, and from a stable species we produce a radical. H is a radical. All right. So this is where you're initiating the chain. You're starting the chain. Then you have propagation reaction. In a propagation reaction, you have the same number of radicals on both the reactant side and the product side. So you have two radicals here, HO2 and H. Again, you have two radicals on the product side, OH and OH. It is just maintaining the number of radicals, not adding, not decreasing. Then you have chain branching, which is where explosion happens, right? You have one radical and one stable species here, and it's giving rise to two radicals, OH and O. So you had one radical in the reactant side, and you are having two radicals in the product side. So this is increasing the number of radicals. Net number of radicals is increasing, and this is an extremely important reaction in combustion. And then at the end, you have chain termination, where two radicals, they combine together to form a stable species. And you can see that there is no radical on the product side. So this is going from something like two radicals to zero. So that's the end of the chain reaction. So these are the four different types of chain reaction. We'll talk about each one of them in more detail with more examples. So let's start with the chain initiation step. As the name suggests, chain initiation reaction is a reaction where the chain starts, where the chain reaction starts, right? And the chain initiation reaction, or the initiation step here, is simply because of the dissociation or breakdown of some sort of molecular species to form unstable or more reactive molecules, atom, or ion. It can be any of those, right? So we're just trying to be very general here. Now, in this reaction, when we talk about the chain initiation reaction, the key idea is that you do not have any radicals in the reactants, but you produce a radical on the product side. Okay, so you go from zero radical on the reactants to one or more radicals on the product side. Okay, let's look at some examples. So let's look at this reaction. H2 plus M. Hydrogen, this is a stable molecule, all right? And M is the third body. It doesn't even take part in the reaction chemically, okay? This dissociation of this H2 molecule giving rise to H plus M. So you're going from zero radical to two radicals, right? So this is a chain initiation reaction. We're going from zero to more than zero. Another example, CH4 plus M, okay? Methane plus third body. Third body can be nitrogen, can be argon, can be helium, can be anything else, right? So something that does not participate in this reaction. Now, the dissociation of this methane molecule is going to produce CH3 plus H plus M, okay? CH3 is a radical and H is also a radical. So again, you're seeing a situation where you're going from zero radicals to two radicals. So whenever you go from zero to more than zero, this sort of a step is the chain initiation step, okay? And this is where the chain reaction starts, okay? You cannot have a chain reaction without the chain initiation. You have to start the chain somewhere. And this radicals, being the chain carriers, are the ones that keep the chain going, but you need to introduce the radicals somewhere, and they get introduced or they get produced from stable species right in the chain initiation reaction. Now, we said that this happens because of the dissociation of some species, whether it's H2 or CH4. But then the question is, what causes the dissociation? What options do we have? Well, there are basically three broad options for causing the dissociation of a certain molecule. Let's say CH4. So what is causing CH4 to break down into CH3 plus H plus M? What is causing this reaction? Well, this reaction can be caused by simply heating, okay? Heating up the methane molecule, which you can heat by putting it in a flame or by using a spark to create a load, a zone of very high temperature where the methane will start breaking down, the molecule will start breaking down, okay, into CH3 plus H. This is one option. Another option could be photolysis. You could use light from a laser or any other source, and or from an electric discharge, and you can basically use it to heat up the molecules. So essentially, when the light is uh, absorbed by a certain molecule, light of certain wavelength is absorbed by a certain molecule, the molecule breaks down because of the energy transfer that's happening. So again, this is another option that you can use for breaking it down, okay? A lot of chain reactions in the atmosphere happen through photolysis, so it's a rather common option. Not so common in combustion, but you can use it, all right? So this is one other option to initiate a chain reaction. Now, when we talk about photolysis or light, it is uh, again, as I said, it's a very, very common reaction. Not so much in combustion, but in general, it's a very common reaction. It's a very common way to initiate a chain reaction. So example being chlorine plus some amount of light is going to break it down into two chlorine atoms, right? So when you do this, it's also called as photodissociation. Okay, so you can dissociate. You're causing dissociation. Now you can dissociate it using multiple ways. Either heat it by any means, spark, flame, or some by compressing it to high pressure and temperature, or you could do photolysis. Okay, any of the two options work. So this is about chain initiation. Somehow you have to increase the temperature or transfer the energy to the molecule such that the molecule will get excited and it will break down. Okay, so that's the dissociation. The key part is the dissociation that's happening. Now that's about initiation. Now let's move on to propagation, which is something that follows the initiation, right? So first you need to initiate the reaction. You need to start the reaction. Once the reaction starts, then you can go to propagation. Now what is propagation? Well, in propagation, the key part is that here the number of free radicals which is consumed in the reactant, right, is equal to the number of free radicals which are generated or produced. Okay, so any reaction, any chain reaction step where the number of radicals on the reactant side is equal to number of radicals on the product side is going to be a chain propagation. Okay, so this is simply maintaining the same number of radicals, right? It is not producing more, it is not producing less, it is maintaining the number of chain carriers, maintaining the number of radicals that happens. And this is the first place where you actually start to see some heat release. Okay, and in the chain initiation reaction, you need energy. All right, it's an endothermic. You need some energy. You need to provide some energy to break it down. But in chain propagation, now it's starting to release some amount of energy. Okay, and basically this is a very key step which leads towards the next, which is the chain branching reaction. Okay, so now let's talk about some examples here. If you have HO2 plus H, okay, both are radicals, two radicals here, HO2 and H. If this gives rise to 2OH or OH plus OH, this is a very good example of chain branching. You had two radicals on reactant side, two radicals on the product side. So number of radicals on reactant and product are same. It's a chain propagation, right? Another example, you have CO, which is a stable intermediate, plus a radical, OH, let me call it star, you're giving rise to CO2, which is again a stable molecule, plus a radical, which is H atom. So you can see you had one radical on reactant side, one radical on the product side. So what is really happening in a chain propagation reaction? Well, in a chain propagation reaction, you typically produce some amount of heat, there is some amount of heat released, and you're typically going from one set of radicals or reactive species to another set of reactive species. All right, so you're changing the identity of the chain carrier. And this is very important because now the chain carriers that we're producing, whether it's OH here or H here, they go on to take part in the chain branching reaction, which is the next step and which is a very, very important step. Okay, so this is all about chain propagation. Moving on, now let's talk about chain branching. We said chain branching is very important, but chain branching cannot exist if there was no chain propagation. So chain propagation leads to chain branching. Okay, now what exactly is chain branching here? These are elementary reactions where you generate more free radicals than you consume. Okay, the key point is that the number of radicals on the product side is greater than the number of radicals on the reactant side. But important to remember, the number of radicals on reactant side is not zero, it's greater than zero. Okay, so this is the key thing that distinguishes chain branching from chain initiation. In chain initiation, all right, in chain initiation, the radicals on reactant side are zero. It's stable species, no radicals at all. You go from zero to a number more than zero, let's say 2 in chain initiation. But in chain branching, you go from a number which is more than 1, let's say 1 or more, to a number more than that, all right, to a number greater than 1. Okay, maybe you go from 1 to 2, or you go from 2 to 3, and so on and so forth. So that's a very, very key point. In chain branching, we already start with a radical. We have non-zero number of radicals, all right? So now let's look at some examples here. So here you have H plus O2. You have H as a radical, stable species, giving rise to OH plus O. Okay, so you're going from one radical to two radicals, increasing the number of radicals, and you're starting from non-zero. So this is an example of a chain branching reaction. Another example, CH plus O2 giving CHO plus O. Again, you're going from one radical, which is CH, to two radicals. Okay, so these are examples of chain branching reaction. In a chain branching reaction, you're growing you're growing the number of unstable species or the reactor species. And this is what results in an explosion, depending on how much energy you release here. Okay, so this is a very, very important step. This is an explosive step, and it rapidly increases the number of chain carriers, right? And the number of chain carriers increases, then that's when the chain reaction starts to move very, very quickly. And this essentially, this branching reaction is something that contributes to the explosion of any combustible mixture. Okay, if you have the fuel and the air in the right proportion. Example being the rapid explosion of hydrogen oxygen mixtures or hydrogen air mixtures. Okay, now having talked about chain branching, let's talk about the end of the chain reaction, which is the chain termination. All right. Now, in chain termination reaction, the radicals that we have on the reactant side are getting consumed, which means that the number of radicals that you have on the reactant side are more than the number of radicals on the product side. So another key point here is that the number of radicals on product side is zero. Okay. So you go from something non-zero number to a zero number, right? In terms of number of radicals. You could think of chain termination reaction to be an exact opposite of chain initiation reaction, right? In chain reaction, we go from zero to a number, initiation reaction. So in chain initiation, we go from zero radicals to a number more than zero, let's say 1 or 2. In chain termination, you go the opposite way. You go from one or two radical species to zero. Okay, so now the key point about chain termination is that the chain ends here, which is why it's called a chain termination reaction. Termination meaning end, and this basically gives rise to stable species. What are the reasons for chain termination? Well, multiple reasons here. Okay, so one is when the reaction is going on and it's towards the end, then your reactants are getting exhausted. They're getting used up, right? So you don't have too many. You have a very low mole fraction of the reactants. And then at such situations, then the free radicals, they cannot go and attack reactants anymore. So what they do is they combine among themselves, right? So free radicals, then they combine among one another, and what they give rise to stable molecules. Okay, and once that happens, when you go to stable molecules, then the chain carriers, which are the reactive radicals, they're gone. Okay, so then the chain ends. Now that is one major way, deactivation of the chain carrier through radical recombination, such as H plus OH plus M, H and OH being the two radicals, combining to form H2O plus M. This is one common way. You could also have H plus M giving H2 plus M. You can see it is exact opposite of the chain initiation, right? This reaction particularly, exact opposite of chain initiation, or the reaction which basically we said was endothermic, and it happens due to dissociation of the stable molecule. So here we are going back to the stable molecule. Okay, this is one way for the chain to be terminated, but there are other ways, right? So another way is that the radical that you have, it goes and hits a wall. It's near the wall of a container, near the wall of combustion chamber, and it gets deactivated, right? It is not able to hit or combining with another stable species and break it down. So it just hits the walls of the container, and its effectiveness in terms of causing more reactions is drastically reduced. Okay, this is one option. Another option is that it reacts with another stable molecule to form an inactive product, which could be a radical, but it's just too slow. Okay, so one example of a radical which is too slow is HO2. Once you form HO2, it's not as reactive as OH or H, so it kind of slows down the reaction. So either we go to a situation where we move towards chain termination by forming an inactive product, or the radical itself it becomes less active because it's hitting the walls of the container. It's very close to the walls of the container. Or the most common scenario where you have radical recombination to form a stable species. The key point is that this is the reaction that consumes radicals. So the number of radicals that you have on the product side is less than the number of radicals on the reactant side. That's a very key point. Okay, in most cases, you go to stable species, but you surely have to reduce. And if you look at it, this is the only reaction where we are reducing the number of radicals, right? As we go from reactants to products. All right. Now, why is chain reaction important? Combustion? Well, chain reaction is extremely crucial for combustion because if you look at combustion, combustion is defined by ignition, which is a very rapid increase in temperature, right? So we have in all combustion reactions have chain reactions. They're composed of the chain reactions, and for a chain reaction to happen, we need to have net production of radicals, which is more than the destruction of radicals for the overall reaction, that is, right? And that's when you can have a stable flame. Okay, and if we did not have chain reactions, then the flame would not be able to sustain itself because you see, when you talk about a flame, you ignite it once, then it stays alive by itself. You don't have to keep igniting, you don't have to keep providing the energy. It it is a self-sustaining reaction where the amount of heat released from the flame will keep the flame running as long as you have the fuel. Okay, so this property, the self-sustaining property of a flame exists only because of the fact of because of chain reactions, essentially. And the key part is that chain reaction are the ones which are responsible for explosions that we see sometimes, and that's essentially because the reaction rate can grow exponentially faster, and that leads to a very quick heat release. Okay, now it will not always lead to an explosion, right? Just because you have combustion does not mean you need to have an explosion, and if you're not having an explosion, does not mean that there is no chain reaction. You can have a chain combustion where you have surely a chain reaction, but you don't have an explosion, and this is something that can be controlled by playing around with how much heat do you release. Okay, so when you're having a combustion process, right? So you're having a situation where you're releasing heat in the chain branching process, right? But the heat can also be removed from the combustion, okay? Depending on what kind of flame do we have, where is the flame located, is there any surface in contact with the flame, so on and so forth. So by playing around with diffusion, convection, or even conduction, you can control the flame temperature, and by removing the right amount of heat, you can ensure that what you have is normal flame. Okay, diffusion simply means the heat transfer to the unburnt fuel mixture. Convection is heat transfer to the surroundings. You could also have a situation where you make the flame sit on top of a metal surface, or the flame is anchored to a certain surface, the burner surface itself, and it transfers the heat to the burner surface, or the heat is removed from the flame. So basically, if you want a situation where you have a flame without any explosion, you have to control how many radicals you have, right? And this can be done, as we said, by controlling the number of by using chain termination in some sense, by having you know having walls nearby, having some sort of surface which can take the heat away from the flame. So it is a very narrow balance, very delicate balance between how much heat you produce and how much heat you remove. And that sort of ensures that that ensures that you have different kinds of flames, right? A normal flame versus an explosive flame. And so this is a very, very important criteria, right? Or a very important balance that exists between the heat the heat transfer that's happening from a certain flame to the surroundings, and the heat release that happens. And this decides the temperature of the flame, and which ultimately decides how quickly you're going to have, or what kind of flame you're going to have. How quickly is the fuel going to get consumed? How quickly is the heat going to be get released? So on and so forth, right? So chain reactions are important. You can have chain reaction in combustion without explosion, provided you treat it, you handle it properly, right? And that's something which is very easily done, not complicated, for a variety of fuel mixtures. It's just that we need to know how to take care of it. Now, when we talk about chain reactions, we got to talk about chain carriers, right? We spoke about radicals being the chain carriers. So then the question is, what are the most important radicals in combustion? Well, the most important radicals in combustion are O, H, and OH. Okay, these are 1, 2, 3, or I would say OH is number one, simply because it's a very, very important radical, always there, always playing a very, very important role in chain initiation, branching, and so on and so forth. CH3 is also a very important radical, always obtained in chain initiation. Okay, whenever you have carbon in the fuel, of course. Now, apart from these top four, top three being OH and OH, OH and OH, right? Three different radicals. Um, and then CH3, you also have other radicals, HO, which could be of interest under certain conditions, HO2 being one. Although HO2, as I said before, is less reactive. Okay. Now, when we talk about chain reactions, chain carriers, we did use the word intermediate, but no, not all intermediates are reactive, right? So CO is not a radical, it's carbon monoxide, it's a stable molecule, but all others, OH, OH, CS3, all of these are they are radical species. They are intermediates, of course, they form in between, but they are also unstable species, and therefore they cause the reaction rate to increase. All right, so that is about different kinds of chain reactions, right? So now we spoke quite a bit about different reactions, and we have an understanding that for a flame, for any fuel air mixture to burn and eventually form the products, for us to go from fuel plus air to products, CO2 plus H2O and others things, let's say A, B, and others, we have a set of reactions that happens, right? It's not just one reaction. And so if you want to solve a set of reactions, which is called a chemical mechanism, you can use a numerical solver like Chemkin with appropriate constraints to solve it, right? This is one option to go about it. And this is something that we actually do for situations where the mechanism is very long and it has large number of species and large number of reactions. Okay. Now, that is, of course, one option, one way to go about it. But let's say you want to come up with a simplistic expression where you simply want to understand what is the key reaction that's going on, how quickly is it happening, or you want to come up with a simplistic expression for describing the key components. Maybe you're not interested in all species, right? Maybe you don't care about all reactions. You simply want to focus on some specific parts. So in such cases, we can we can go with two options. One option is we come up with an empirical one-step combustion mechanism. Okay, so instead of having multiple steps, you just come up with one-step combustion mechanism, right? And this will define the way fuel plus oxidizer is getting combined to form the products. This one is an empirical mechanism, right? So it's empirical, meaning it's derived from experimental data, which means that it can only be used for the conditions of the experimental data. You cannot use it outside. But why do we care about it? Well, when you're solving fluid flow, when you're trying to solve fluid flow plus energy equation plus combustion, which is a reaction, then sometimes or a lot of the times it is very convenient to have less number of reactions, because the more number of reactions you have, the more equations you are solving, and that simply complicates the whole numerical solution. So if your geometry is large, it's complicated, like engines, gas turbines, and others, we may want to look at one-step combustion mechanism as a way to understand broadly what is happening and as a way to solve for it. Okay, so this is the reason we use it, and yes, it has its own constraints, but it is one option to go about it. Okay, the second option is when you say that, all right, one step is too narrow, it's too simplistic, then what you could do is you could look at the reaction that you're trying to solve, and you could simplify it, a subset of a reaction. You can simplify it by making certain assumptions, which make it which keep it fairly realistic, but also will give you more insights into what is happening. So you could these assumptions or the simplification that we apply could involve maybe assuming that you just have a forward or a backward direction only in a certain elementary reaction, instead of assuming it to go both ways, because in reality elementary reactions go both ways, right? You could say, okay, it's not happening in one direction, it's just happening in the forward direction. Okay, which means that you can use it to reduce the number of unknowns, and you can use it to simplify the equation set that you're solving. You can also do what's called a steady state approximation, meaning you can say that a certain species, its concentration is not going to change. Okay, it's not going to change with time. So you can do that. You can also do what's called as partial equilibrium. So there are multiple options, and we'll talk about each of these options in more detail in the lecture in the coming lectures, right? So what I want to tell you till now is that I want you to understand what are the different types of chain reactions and have a very good understanding of the difference between the different kinds of chain reactions and what they mean. And chain reactions are an important part of combustion, and we'll see more as we move forward. And lastly, if you are dealing with a simple geometry, then you can, solve a numerical, you can solve a kinetic mechanism using Chemkin, which is brilliant for a 0D chemical reactor, okay, or a 1D chemical reactor, like a flame, like a Bunsen burner flame, or like a flat flame or something like that, where it's very simplistic. But if you go to more practical situations, then you don't really want to be dealing with a chemical kinetic mechanism which has 100 species, 1,000 reactions. That's just not feasible, right? So that's why we will spend time looking at these two options as well, which are again very practical, very realistic. They have their own limitations, of course, but they still make sense in a lot of cases. Okay, so stop here. See you in the next class.